This conference will now be recorded.
Welcome, everyone. Today we have Mark Weiss to present to us clock and oscillator statistics and characterization techniques. Mark is a mathematician, and he worked for years in NIST Boulder Laboratory on controls and experimentation to demonstrate of like time transfer over commercial telecommunication networks. And the experimental equipment in his room on the room of locks into NIST official versions of international time, transfer time signal back and forth between NIST and US Naval Observatory time services in Colorado Springs, and measuring system time transfer accuracy. I think without further ado, let's jump into the presentation. Mark, the floor is yours.
Thank you. Thank you. So as Ahmed said, I worked at the NIST Time and Frequency Division for 35 years, and I'm going to be talking about a number of the techniques that were developed by NIST for characterizing clocks and oscillators. And so this is sort of standard stuff that they all, a lot of people worked on. I guess a number of the more prominent people that taught me all this were, David Allan, Sam Stein, I can't remember all their names. There was a guy from HP who was a fellow and developed the famous HP clock, cesium clock, and so forth. So that's where all this stuff comes from. So the model, so there's going to be two parts to the talk I'm giving today. I'm going to talk about the models, and the model is both for clocks and for time transfer systems. They both use more or less the same model. And there are two parts to the model. There's a systematic part and stochastic parts. And I'll talk about that, and phase or time versus frequency deviations, and I've got examples. This talk is actually from a seminar that NIST gives every year. They're still doing it every year on time and frequency. I gave this at NIST for, I don't know, 20 years every year. And this is an abbreviated version of it because this talk was a couple hours or more. So we'll start out with, so part one will be the model, and part two will be how to characterize clocks using variance analysis. And there's essentially three variance or deviations that I'll present: the Allan variance, the modified Allan variance, and the time variance. They're all very related. Okay, a first concept that is really important and people confuse a lot is the difference between accuracy and stability, or accuracy and precision. You know that if you look at a target and you're trying to shoot at a target, you can be stable or precise, but not accurate. If all the bullets are in one area, you can be neither accurate nor precise if they're spread all over the place and the center is not the center of the target. You can be accurate but not precise if you've got bullet holes all over the target, but they're centered at the center of the target. And if you look at the plot below that, that's what time measurements look like that are accurate but not stable. They move around a lot, but in the long-term average, they average to 0. And of course, accurate and stable means that there's not much noise, and they average to 0. And the other thing to always keep in mind is when you measure a clock, you always measure it against another clock. You never just measure a clock. And so you're always looking at the difference between two clocks. In what you want is to have the reference clock be much more accurate and much more stable than the clock that you're measuring. But there's always the noise of both clocks and the inaccuracy of both clocks in any measurement. So a systematic deviation, that's important. That means that the deviations are completely, so again, it's a deviation from the reference. Always it's against the reference. So the clock under test, the measurement, the clock you're measuring deviates from the reference clock by a systematic way, which means that the deviations are completely determined once you know the initial conditions, or stochastic or random means that they're unpredictable except in a statistical sense. So here's the model. It's really simple. There's three terms that are systematic. There's the initial time offset, the initial frequency offset, and then there's this, what we in the timing community call drift, is linear frequency drift. I know a lot of folks call drift what I'm calling the frequency offset. So there's some language differences. I'm always going to be talking about the linear change in frequency in a very systematic way as drift. And then all the random or stochastic stuff is in this epsilon term. I don't know if you can see my arrow, but the epsilon is all the frequency, I'm sorry, all the random or stochastic terms, and there are 5 random types that we use for characterizing clocks. Okay, systematics, there, as you saw, there's a frequency offset, there's a linear frequency drift. There can also be environmental dependencies. I'm not going to talk much about those, or shock, radiation, vibration systematics, or or gravitational systematics. So here's the example I'm going to be using. This is actual data from NIST of hydrogen masers. I know hydrogen masers are not commonly used, but it's what I have from my talks at NIST. You know, most people can't afford or don't have a reason to buy a hydrogen maser. They're like $250,000 each. But we use them at NIST as sort of the basis of our timescale, and that's why I show them here. So, but it could be any clocks, and if the clock is dominated by a time offset and a frequency offset, it basically looks like a straight line, which is kind of what you see here. And the origin at the left of the screen is not 0, so that's a time offset at the beginning of the measurement. And there's a rate offset, which is why there's a slope. You know, it's not flat, so that means there's a frequency offset. And if you stare at it hard enough, you can almost see that it's actually parabolic. But you got to take my word on that because you can't really see it. And that means that it's dominated by a linear frequency drift. So what I'm plotting here is just the difference in time between two clocks. That is, each clock, it has a time reading, if you will. You could think of it as a 1 pulse per second output with data that says what the time is at the time of that pulse. And so this is the difference of those, and it's measured over days of the year. So the second thing I'm going to plot is the frequency offset between these between these clocks, and you can determine that frequency offset by taking the first difference of the data. So if the measurements, the actual measurements are these x sub n at a reference time t sub n, if you difference them, you take the difference of neighboring points, and then divide by the time interval between those points, you get the average fractional frequency offset over that time. And note that these data are unitless. We've got time divided, measurements in time, say nanoseconds, divided by time interval. And if the time interval is in nanoseconds and the data are in nanoseconds, the fractional frequency offset are unitless. So I'm going to go back one slide. So if we look at exactly these same data, but we look at the first difference, the frequency of those data, it looks like this. And now you can see some actual variations on it. And you can also see the slope of the frequency. So there's a linear frequency drift so you see it wandering up to the right in almost a straight line. And then you see noise around that. The noise around that is the stochastic noise of the hydrogen masers. So there you see all the parts of the model. There's the time offset, the frequency offset, and the noise. And now if you take away, if you remove a constant frequency, a constant straight line, so you take out the mean and the average frequency from the original data, what it looks like is a parabola. So that is the linear frequency drift that's dominating these data. Okay, and now if you remove a quadratic from the original data, what's left is the stochastic data, but the stochastic data in time, and so you can now see the variation due to these stochastic data. And if you plot as a frequency, the frequency data, right? I'm taking the first difference of time to get frequency. Now you can see very clearly the kinds of stochastic noise. And if you stare at this, you can see that there's what you might call jitter, a high frequency noise that has a mean, but then there's also kind of a wander where it's walking away from the original frequency offset. So that's because there are different types of frequency of stochastic noise. And so I'm going to talk about stochastic noise now. So these are the different kinds of stochastic noise. There is white noise, white noise variations around phase or time, which we call white phase modulation. There's also a kind of a wander called flicker noise. And then there's a random walk in phase, which turns out to be exactly the same as white noise around frequency. And then there's flicker in frequency and random walk in frequency. So there's really three concepts that we're going to have to understand: white noise, flicker noise, and random walk, and how they're related. But there's white, flicker, random walk in phase, and white, flicker, random walk in frequency. But random walk in phase is exactly the same as white in frequency. So there's really 5 noise types. Okay, so what's the math behind this? Well, you know what a sine curve is, right? You've got if you've got a pure sine curve, there's an amplitude, which is the V0, and then there's a frequency or a period, which is the new zero, in the parentheses, which is times t, and then there's this capital phi of t, which is the residual phase deviations, and that's the phase noise. And the frequency deviation is really just the derivative of the phase noise. And you can also see the normalized fractional frequency deviation as the instantaneous frequency offset from the nominal frequency divided by the nominal frequency. And you get the time deviation as the integral of frequency deviation. So here's some illustrations of what these different noises look like. And this is just, I just generated this stuff. So if you have white noise on phase and it's on top of the sine curve, so you've got a frequency and there's noise on a frequency, this would be a very, very noisy clock if this was the sine wave it was putting out, but it's white noise on frequency, and the noise in the phi that I added to that looks like this. And your eyeball is really good at determining the different noise types, because if you look at this, you can see that it's jumping around a zero, that every instant of measurement, there's an impulse that moves away from zero, but the next impulse is completely uncorrelated from the previous one. Now, flicker noise, it's kind of trashing the sine wave more. And here's what it looks like. And if you look at that, you see that it's kind of wandering away from zero, but kind of slowly. A random walk in phase looks like that, and it walks away, which is why it's called a random walk. And ultimately what it is there's an impulse, the same as a white noise impulse, but the impulse of at each time starts from the last, where the last impulse left off. So you're literally walking away with a randomness. So a way to understand white versus random noise, right? Suppose I have a coin and I've got it's a fair coin, which means that any flip of the coin is completely unpredictable, totally unrelated to what the past flip has been. Exactly 50-50 chance of getting a head or a tail. And every time I get a head, I take one step forward. Every time I get a tail, I take one step back. Every step I take is exactly the same size because I'm perfect in the way I'm giving my steps. And so let's see. So what you expect, the expected position after n tosses is that you would be the square root of n steps away. And then you can talk about the spectrum of these data, the spectrum of a random walk process. It means that you look at the Fourier transform of it and you square it to get power, and the spectrum, the Fourier spectrum, goes as f to the -2. So you see, this is sometimes called red noise because as frequency goes to zero, at lower frequencies in light are more red in the visible spectrum, and more, the higher frequencies are more blue. So as the frequency gets smaller, the power gets much larger and goes to infinity at zero. So there's always a low frequency cutoff in reality, even though the spectrum may look like f to the -2. And the first difference of a random walk process is white noise, which has white noise, the spectrum. White noise means that the same power over the band of all the frequencies in the data. So that's why it's f to the 0. The same power for all frequencies in the band. And why is this not? There we go. So you see that white noise is a series of random uncorrelated impulse. Each impulse is an offset from the same mean value. A random walk, each impulse starts from the last position that you were in. So with our coin flips, each step starts where the previous step left off. Flicker noise, and so what you can see is that if you have a system that's being given random impulses in its state, the state of the system is changing in some random way, and each impulse is random uncorrelated, but the system changes. It's got this impulse, it changes in a certain way, and now the next impulse starts where the last one left off. The system is going to experience a random walk in the way it's changing. And that means that it's got a memory of where the last impulse, what the last impulse did to it. Now, if the memory, if the change that this impulse does to the system gradually decays, then you get something more like flicker noise, where the next impulse happens before the previous impulse has decayed to zero, but it doesn't have perfect memory, but it doesn't have no memory. It's between white noise and random walk noise. A really good example of that is if you have an iron bar and you hit one end of that iron bar with random uncorrelated changes in temperature, and the temperature propagates down the iron bar, but as it goes down the iron bar, it radiates some of that temperature, so that impulse, it forgets what the impulse was at the end where it's being changed. At the opposite end, the changes in temperature in the iron bar will be exhibit flicker noise. So that's an example, a way of understanding white noise, flicker noise, and random walk. And now remember that if you have frequency and you integrate frequency deviations, you get time. Exactly the same way if you have white noise and you integrate, or in the discrete domain, you sum, you get random walk. So that's why white frequency noise is exactly the same as random walk in phase or time, and vice versa. If you differentiate random walk, you get white. If you differentiate time, you get frequency. So that's why white phase noise, so this is data that's white phase noise, and here's what the 5 noise type visually look like. And you know, if you're used to looking at these data, you can just about look at a data set and know what noise type dominates just by the way the data are moving around. And if you look at the very bottom one, the random walk in frequency, it almost looks like a parabola over different periods of time. And so a random walk in frequency is very difficult to differentiate from a linear frequency drift. Okay, so that's the model, right? We've got the model, we've got the accuracy versus stability, we've got phase versus frequency noise. Now I'm going to talk about how you characterize these things using the Allan deviation, which is the square root of the Allan variance, and then why they came up with the modified Allan deviation, and why we also have the time deviation. So the problem with the reason we need a different kinds of variance than the traditional statistical variance or standard deviation is because if you're looking at data that is not, whose noise type is not white, the standard deviation is really just a function of how long you measure. There is no mean, so there is no real standard. You can't, if you take the standard deviation of a data set that's walking away in time, the standard deviation just gets worse the longer you look. So what David Allan came up with is this idea that what we're going to look at is the slope between neighboring points. So here are 3 points in this data set, x1, x2, and x3. If you look at the slope between x1 and x2, we call that y1. And if you look at the neighboring interval of the same length, so this is, you see, we're going to get a variance as a function of this variable tau, which is a time interval that you're of interest. So you can call it the averaging time that we're trying to get the variance as a function of this averaging time. And so x2 minus x1 divided by tau is the average frequency between time 1 and time 2. The same thing is y2, the average frequency between x2 and x3. So that is the two different slopes here, and the difference in those slopes, y2 minus y1, is an estimate of the instability of this clock. How is the frequency changing as a function of tau? And so we take the difference over two neighboring intervals of length tau, we square that. That's what this means down here. We take the square of the difference in neighboring frequencies over a time interval tau, and then we average that square over the full data set. That's the Allan variance. And it turns out that that has a power law, and from that power law, we can determine the spectrum, the spectral power law. So here's how you can compute it using the time data, right? If we go back here, you notice that the difference between these frequencies is the second difference of time. x3 minus x2 minus x2 minus x1 divided by tau is exactly what we've got here. And it turns out to be x3 minus 2x2 plus x1 is the second difference. You square that, sum it over the data set, and divide by the number of points as well as by the tau value and everything squared, and you take 1/2. So if we go back and look at what definition was, it's 1/2 of the mean of the change in frequency squared. So that's where this equation comes from. So why are we doing that? So again, if the time data looks like this, it's walking off, and over this interval tau, you get average frequencies that look like this, and they're walking off. If you did the standard deviation of this set of frequencies, it would not converge. The longer you look, the larger the standard deviation gets. So it really doesn't tell you much about the clock. The standard deviation of a data set doesn't tell you much about the clock. However, the Allan variance does converge, or the Allan deviation does converge. And it turns out that these kinds of noise types are in everything. It's not just clocks, that any physical measurement you make, everything, every system that you measure changes with time. And therefore, a measurement, the longer you look, it's going to change with time. These kinds of noise types were popularized some years ago. There was a book called The Fractal Geometry of Nature by Mandelbrot, and he generated images that looked like natural forms just by having these kinds of noise types in the data, just by drawing an equivalent coastline where the coastline had flicker noise. So if you take the Allan deviation of noise, it turns out, and plot it on a log-log plot, it turns out that the slope of the data, the slope of the Allan deviation, gives you the noise type. If the noise is one of these power law spectra. If you've got white FM, the Allan deviation drops as -0.5, where the Allan variance is the square of that, so it drops as a -1 slope. Flicker noise shows frequency noise as a flat curve, and a random walk in frequency shows a +1 slope. And a linear frequency drift is also apparent, and you can see that it goes as a +1 slope on deviation or a +2 in variance. So there's a problem with the Allan deviation because white frequency noise and flicker frequency noise have the same slope of a -1 slope on deviation or a -2 slope in variance. And there's a direct formula for translating from the spectrum. So here's this capital S sub phi of F is the spectrum of the frequency of the, I'm sorry, spectrum of the phase noise spectrum. And if you, this is kind of a transfer function, the sine to the 4th power. If you integrate the spectrum against the sine to the 4th of this term, you get exactly the Allan variance. So there's a direct translation between the Allan variance and the spectrum, which is where you get, and there's also a drift term. The drift appears as a +1 slope. And so going back to our example, remember this is what the frequency data looks like between these two masers. If we compute the Allan variance or the Allan deviation of this, you see here's the +1 slope on the log-log plot. And so this dominates the long term, and that means that we're looking at linear frequency drift in long term. In short term, it might be flat, which would mean flicker frequency deviation, but we have to deal with the fact that the linear frequency drift is dominating. So we estimate the linear frequency drift by...
Mark, I think in telecommunication, we use T-dev, not Allan variance anymore, correct?
That's right. That's right. But T-dev is a function of Allan variance, and Allan variance is kind of the beginning point of understanding these. So I'm going to get to T-dev. It's just a couple of slides away, in fact. So I'll take questions soon, and we can go back through whatever you need. Here, just again to see how the Allan variance, oh dear. How do I get down here to where I was? Okay, here's where I was. I was here. And then if you take the Allan deviation of the data after removing the linear frequency drift, what you see is that long term, these data are dominated by flicker FM, all the way out from 1 day to 10 days. The data that I'm showing you, the short term are 1 data point per day. In long term, there's an uncertainty. These are the error bars around the Allan deviation. And so if you draw a line through the data, you more or less get a flat slope, and you say, okay, so these hydrogen masers are dominated by flicker frequency modulation all the way out to about 10 days. And the level is about 2 parts in 10 to the 15. That tells you a lot of information about the hydrogen masers, how you expect them to walk off from each other, and how fast they should walk off in time. Now, because the flicker phase and white phase modulation, because the Allan variance doesn't differentiate between these two, Dave Allan came up with another model another variance concept, and it's kind of the same thing as the Allan deviation, where we're taking the difference of phase, but instead of taking the difference of phase between two individual points, you first average the phase over an interval tau, and then average the phase over another interval tau, and the third interval tau. And so instead of points x1, x2, and x3, we have average point x1, x2, and x3, and you take the second difference of those, which is, again, it's the difference of frequency, but now you're sort of pre-filtering the phase data by averaging it over intervals tau, and that makes it differentiate. So this is the equation for that. It means that there's a double sum. Computing it takes a bit longer because you get going as the square of the data set of the size of data instead of just the size of the data. And now what happens on a deviation plot is that white noise drops as -3/2, flicker noise drops as -1, white phase frequency noise or random walk-in phase drops as -1/2, flicker frequency noise is flat, random walk is +1/2, and the linear frequency drift is +1. And so now we've got this, it's almost like a super fast Fourier transform. If you know that the Fourier spectrum is a simple power law, right? The spectrum goes as f to the mu, let's say, or f to the, what do they call it? F to the alpha is the letter that we typically use. So if the spectrum goes as f to the alpha, this allows you to determine the value of alpha as well as the amplitude by simply doing this modified Allan deviation. Okay, now what I want you to notice here is that the flat part is frequency, flicker frequency, and things are coming down before that and things are going up after that. And if you wanted to focus on phase noise, it's a lot harder to see where the breakpoints are. And the breakpoints are really important for understanding how the data work and for doing cool things with the data, like optimally filtering them. Like if you were trying to do a phase lock loop, you really want to keep averaging down the phase, but if you go past where it's white into flicker noise, you can't average anymore. It doesn't do you any good. So you really want to find this point here. It's a lot easier to find the breakpoint where it's going down to where it's flat. And so if you wanted to focus on phase noise, it would be really cool to be able to just tilt this sideways. And if you think about what the equation is, if you could multiply all of this by tau, that would tilt it. And that's exactly what the time deviation does. Well, before we do that, here's the power law spectra on the right for frequency or for phase, and the Allan deviation and the modified Allan deviation slope on a log-log plot. And so the relationship is that mu equals -alpha -1, where alpha is the spectrum of the frequency and mu is the slope on a log-log plot of the modified Allan deviation. So that's very cool. It simplifies a way of characterizing all these noise types, but you know, we still want to talk about how do you get how can we see phase noise better? And so if you take the modified Allan deviation, this is the modified Allan variance, multiply it by tau squared, that's going to tilt that whole curve by a factor of tau. We divide by 3, which makes the short term look exactly like the standard deviation if you've really got white noise. And So here's the time deviation. So this is TDEV, which is what's used in the telecom industry. It's actually a standard in telecom, as the gentleman commented. So now, if we're focused on, if we want to know what the phase noise types are, this is a really good tool because you can see where white phase noise dominates and then flattens out at some transition point where it goes from a -1 slope to a 0 slope. For example, if you're trying to do a phase lock loop, you want the attack time to be right about near that transition, because any averaging beyond that doesn't do you any good. And you certainly don't want to go past that where you're in the random walk regime and the phase noise is just getting worse. Okay, so here's an application for time and phase. So one of the things we did at NIST is we compared the UTC from NIST against UTC in other national labs using GPS Common View, and we did it with, with Common View, you're looking at one satellite and the measure of that satellite against UTC PTB, which in Germany, or UTC NIST in Colorado, USA, and you look at it via different satellites, you actually get a different answer because of biases in the satellites. And so what's the optimal way of combining these? Well, if you combine them and you look at the average noise, the phase noise, you're able to see that the noise is flicker noise from 1 to 2 days, which is probably measurement noise because clocks exhibit frequency noise, not phase noise, which means that at about in these data, 1 day, 2 days, 4 days, you begin to see the actual clocks. So if you had these data and you want to know what the actual values of UTC PTB versus UTC NIST were, you can't see it until you're looking at about 4 days. Shorter than 4 days, you're just looking at the measurement noise. So there's an example of why you might care about this and how you can use it. And it's not just masers or these very stable clocks. If you look at quartz oscillators, you have exactly the same problems. And in addition, you can look at periodic effects, that TDEV responds to a pure sine wave with a kind of sine x over x curve. And if you have a white phase noise with a periodic, you see a maximum, and it's possible to differentiate what is a periodic. Typically, if you just have white phase noise and you want to know what the periodic is, you do a Fourier transform, find where the bright line is in the Fourier spectrum, and that would give you the period. However, if you've got a red noise, a pink noise or red noise, and so it's not white, you can't do a Fourier transform. It gets wiped out by this red noise, and you can't see the periodic, but you can on an Allan deviation or a TDEV or a modified Allan deviation. So here's the range of applicability for different noise types. A quartz oscillator, you see, exhibits all 5 noise types. If you want to focus on phase noises, like in the telecom network, TDEV is much more useful. ADEV is pretty good for most of the atomic clocks. And so the summary is ADEV and MDEV focus on clocks. TDEV focuses on time or frequency transfer systems used in telecom specs, as the gentleman mentioned. MDEV distinguishes white phase noise from flicker phase noise. ADEV maps variances, power law noise types into variances. That's my talk. Thank you for your attention. There's lots of extra slides in the PDF. and I can take questions.
The relationship between TDEV and MTI.
Oh, MTI gives the maximum time error. So if you looked at those phase noise plots, you say, what is the maximum variation in the data? Let's see if I can get back here. And so, for example, I need some actual data here where we can look at stuff. That's frequency. We want time data. Yeah, here, this one. So this is time data. If you, why does it do this? This is the one I want to look at. Come on. If you're, except it's not time data, it's frequency data. I'm just trying to make this simple, but it's getting too complex. Okay, so if you look at a time interval of, say, 5 days, each major line here is 5 days. What's the peak-to-peak variation over any 5-day interval? And you find the largest variation over a 5-day interval, that's the MTI of these data as a function of 5. As a function of 1 day, you look over shorter intervals, at 10 days, longer intervals. TDEV, on the other hand, is a second moment. You're looking at the square of the data. So, and again, you're looking at the variation of the square of the frequency data. So MTI is the maximum time interval. TDEV gives you the maximum of the frequency data as a function of tau squared, of the frequency squared. That answer the question? I don't know.
Yes, thank you. Thank you.
Yeah. What else could we talk about? Any other questions?
So one thing before we go through a question, just everyone keep in mind we have the second part of this presentation basically coming in on the 21st, so in 2 weeks. So
yeah, it's a different topic. It uses these characterizations and talks about how to optimally combine clocks to get a timescale ensemble.
So one more question, probably I want to ask Mark. When it comes to holdover, what's our best measurement, let's say, to show the holdover performance?
So that's a really good question. What you want to do with holdover is optimally predict what the next data point's going to be if you no longer have your reference.
Yeah.
So if you can characterize the performance of your local oscillator against the reference, so your local oscillator is locked to a reference clock, right? And you're just following the reference. You know, we used to call it master slave. We're trying to get away from that language and just say follower leader. So the reference clock is the leader. You're following, and then you lose your reference. What's the optimal thing you can do?
Yeah.
Okay, so if the noise type is white phase or flicker phase, then what you want to do is average the frequency over a long period of time, because the frequency is not changing. It's simply phase noise that's changing. On the other hand, if you've got a random walk in phase and white noise in frequency, you want to take the last slope of the data, which is the optimal prediction. And so the holdover algorithm that people implement for determining what to do with the local oscillator, you want to use your memory of the frequency and the memory of the phase that you've integrated against the reference. And depending on the noise type, you lean toward the latest frequency longer instead of averaging longer, or you lean toward the latest phase instead of averaging longer. Does that make sense?
To a certain extent, however, like what I want, like I'm thinking about it in a practical perspective, right? So you have, let's say, the lead and the follower. So then as you're going through the process of synchronization, you basically do some fine tunings to do the synchronization to your to the lead,
Right,
right? And then
right.
now you lose connection, and then you stick to the last correction that you had and you continue on that. But then
Yeah, but you see your correction, the way you're locking your oscillator, you have a you can do a PID lock, right? So you can average, you have a long an averaging time, which is
yeah,
just essentially averaging the phase, and then there's an average of the integral, which is essentially averaging the frequency. And you adjust those depending on what the noise type is.
yeah. Yeah, but then often we see, like in a practical perspective, we see that every time we run this, we have like another different random walk. Like there's a random walk of like the deviation, because there's always imperfection in the synchronization. Plus the lead clock itself is also getting like a reference as if from the GNSS or something from another higher
Right,
level thing.
exactly.
Yeah,
So the follower clock gets a signal. The
yeah,
noise on that signal is a combination of the noise on the lead clock. The
yeah,
lead clock, you could characterize exactly what of these 5 noise types. It's not just random walk. Is it random walk in phase, random walk in frequency? Is it white noise, flicker noise? You can characterize what are the power levels of the lead clock, and then characterize what are the noise types of the transfer system. And that's
yeah,
exactly the example I showed. And
yeah,
once you've got that characterized, you can optimize how you lock your follower to the signal it's getting.
yeah,
And that's what gives you the optimal holdover. If you've
yeah,
optimized what the noise is that you're getting, if you characterize the noise, you optimize your lock, and now
yeah,
when the signal goes away, you've got the optimal prediction.
yeah. Is there also this the short-term stability versus long-term stability here? Of course, like that reflects back to those types of noises, right, that you mentioned?
Exactly. At different times, different averaging times, different noise types dominate. Typically, you get this bathtub curve that I showed, where when you do the Allan deviation, or the modified Allan deviation, or the TDEV, you get this curve where it's going down at short term, flattens, and eventually goes up. Every physical system does this, not just clocks. And different things have, different levels. Some of them, you never even see the white phase noise. You just see the flicker frequency noise. And some of them you never see. For example, a GPS receiver in long term you'd probably never see flicker FM. It would only come down, but in long term it would come down slower.
Yeah. Thank you. Anyone else? Any question?
Yeah, I have a question. Hey, Mark, it's great to see you. Kevin here. So you were just talking about in terms of holdover, we have the model. We characterize the leader, we characterize the follower. Based on that characterization, we can have an optimal method for holdover. But the time transfer in particular with 1588, for example, that seems to introduce or has the possibility of introducing errors in time and frequency that are were not really the scope of the Allan variance and TDEV and all of these models in the past. And any comment on how to incorporate the time transfer into this coming up with a solution, especially in terms of holdover?
That's a really good question. The time transfer can be characterized using TDEV. But the problem with things like PTP is the packets have a huge variation. You know, if you look at the PDV, the packet delay variation, there'll be these so-called lucky packets that come through very quickly, and other packets get you know, as a packet goes through a network, if it's going through devices that are PTP unaware, right? They get stored and forwarded, and some of them go through very rapidly. Some of them get delayed a lot more, and so you get different bands of noise depending on which delay you're looking at. And PTP devices optimally do a packet selection before they even begin to lock to them. And so what you do to characterize it, they've come up with other forms of TDEV. So here's TDEV on my graph here, and what they do is they do a sort of pre-filter of the data, and there's a band pass TDEV, there's a min TDEV, which gets, you know, a minimum delay. So you look at what was the delay. You look at what's the delay on that packet, and allows you to pre-filter, and then within a band you can characterize, okay, this band of PTP looks like this band of PTP looks like that. In my example, you know, I showed different satellite data, and if you do the TDEV of that, you find that the time transfer has a certain noise, and you can differentiate what the clocks are doing from what the time transfer noise is. Typically, time transfer noise is going to be white phase noise or flicker phase noise, whereas the clocks themselves will start with white frequency noise. So you're able to differentiate it. You get a beautiful picture of what are all the different pieces of the puzzle by doing this.
Yeah, thank you, Mark.
You're welcome. It's after the hour. I guess I've filled up the time.
Mark, can I ask a quick question? It'll be super fast.
Good.
I'm not in a hurry.
Okay, I was just wondering if you had a recommendation for a good mathematical treatment of the talk that is summarized here, somewhere you can go to dig into all the mathematics that has all the pieces in one place. I've tried to penetrate it in the past before, and my brain was scattered to all the places I needed to go to understand it all. So do you have a recommendation for that? That's my only question.
NIST has a book they put together of all the best papers on clock characterization, and it's a tech note, and you can get it from the NIST website. What I'd like to do is put it on the chat, or maybe is there some way I can post it later?
Yes. for sure.
Because it's
We'll
not
just
it's
add
not
it
in my
basically.
PDF and it's not in the talk.
We will add it as a separate PDF, or you have it in a PDF or a link. Yeah, we'll add it
It's
there.
going to be
as
one link. Maybe I'll just add a PDF of references.
Oh, that would be great. Thank you.
Yeah,
Thank you.
thank you. I'm sorry, I'm actually meant to do that, and I just didn't get around to it. So,
Or you can do this, Mark. You can add it to your PDF. Send me an updated one.
okay,
Your
I'll do it.
presentation. That's easiest.
Yeah, that would be good.
Yeah.
Great.
Any other question? We don't want to leave anyone behind.
I covered a lot of things quickly. It's not familiar to a lot of people, and it can take a while for it to sink in. So,
Yeah.
if you have questions later, you can email me. I think my email is on the first page of this, the slide.
Right? Yeah. If not, again, you can add it in the revised version you're gonna give us, so we're gonna put it there for everyone.
Great.
Okay. Thank you, everyone. Thank you, Mark. It was great, like usual. Like always, great talking to you.
Good
Okay.
talking to you, Ahmed.
Thank you. Okay. So bye, everyone.
Bye.
Bye.